In traditional reinforcement learning setups for language models, policy gradients are computed directly over raw token sequences sampled from an autoregressive distribution. This schematic visualizes the baseline assumption of standard open-source RL frameworks like Virl and DeepSpeed Chat. They expect a direct synchronous mapping where a flat prompt sequence possesses a one-to-one relationship with the generated output tokens. But modern AI agents deployed in complex environments do not operate on flat prompts. They run inside stateful software environments known as inference harnesses. Frameworks like OpenClaw, Codex, and Claude Code are standard examples of this architecture. A harness provides rich runtime scaffolding. It manages multi-turn reasoning loops, injects necessary tools and file system permissions, and coordinates communication between specialized subagents. To accomplish this, the harness physically manipulates the context string between turns. It might prune older interaction steps or inject dynamic JSON schemas based on active permissions, doing all of this before the primary language model ever sees the input. While this inference scaffolding substantially improves task completion in production, it creates a structural barrier for reinforcement learning. The trainer is built for flat, predictable sequences, not dynamic, stateful software environments. This creates two distinct technical constraints. The first is a software barrier. In a stateful harness, the raw agent observation undergoes opaque internal software transformations. We see the observation pass through dynamic tool schema filtering and context pruning to respect window limits. It emerges structurally transformed into a much larger, complex context block. Because standard RL trainers assume full visibility into the prompt history, this manipulated context completely blinds the training framework. The secondary bottleneck is a hardware barrier. Running interactive agent rollouts requires highly realistic computing environments. A true evaluation of an agent means executing tasks inside interactive bash terminals or navigating web browsers via headless displays to render full desktop operating systems. These containerized sandbox environments demand heavy CPU and memory allocations. If you attempt to co-locate these sandboxes with high-throughput training GPUs, you trigger resource starvation and latency bottlenecks that stall the training pipeline. Because open models cannot be trained within the actual harnesses they are deployed with, an artificial performance gap exists between open-source weights and frontier closed-source agents. OpenForgeRL resolves both the software and hardware barriers by introducing an asynchronous interception proxy architecture. This design physically separates environment execution from policy optimization. This diagram displays the three interconnected subsystems that make up the decoupled architecture. On the left is the Kubernetes rollout orchestrator. This orchestrator spins up hundreds of isolated Docker environments across cloud providers. It uses inexpensive CPU instances to handle the heavy sandbox execution, booting a clean environment for every task instruction. On the far right is the GPU trainer engine, handling policy weight updates asynchronously. The crucial middle layer linking them is the HTTP interception proxy, acting as a transparent middleware endpoint mimicking the standard OpenAI API. By acting as a remote telemetry link, this decoupled design allows the training cluster to scale horizontally on high-end GPUs, while rollout sandboxes execute concurrently across hundreds of CPU instances simultaneously. During a live task, the proxy server actively buffers the harness's internally formatted prompt and the model's chosen action. It pairs them into individual step records. When the harness finishes its multi-turn loop or reaches its maximum allowable steps, the system triggers terminal execution. An automated verification script runs inside the container sandbox. This script physically verifies ground truth state changes. It checks for modified file hashes or updated database entries to assign a strict binary terminal reward. The terminal reward is transmitted back to the proxy, which compiles the individual step records into a unified Markov decision process trajectory, queuing it for the GPU trainer. To correctly compute policy gradients from these asynchronous requests, the proxy engine applies exact loss masking. This diagram shows how exact loss masking operates. Harness-injected context and system tool definitions receive a loss weight of 0. Only the generated bot tokens and structured tool call arguments receive a weight of 1. This specific masking mechanism guarantees that the policy gradients are computed exactly over the opaque prompt distributions the model actually faced inside the production environment. Training these agents presents an additional mathematical instability. Traditional parametrized value critic networks struggle to predict delayed terminal rewards accurately over long-horizon language tasks. OpenForgeRL completely bypasses the critic network by utilizing an alternative strategy, Group Relative Policy Optimization, or GRPO. The core mechanic of GRPO is straightforward. For every query, the policy samples a group of 8 parallel rollouts, executing them inside the target harness. Instead of using a separate critic network to guess a value, the algorithm evaluates success by computing the advantage relative to the mean and standard deviation of the rewards within that specific group of 8. If the agent faces a highly difficult task where only 1 out of the 8 rolled out succeeds, that single success yields a significant positive advantage compared to the failed group mean. Unlike standard methods that struggle to assign value across tasks of unequal difficulty, this relative evaluation naturally discounts the variance across the dataset. GRPO focuses the learning updates precisely on rare discovery events across stochastic execution sandboxes, achieving stability without an unreliable value critic. A final barrier restricts reinforcement learning in domains outside of raw coding, such as desktop GUI operation and live web browsing, a severe shortage of reproducible training sandboxes. To solve this data scarcity, OpenForgeRL implements an automated 5-stage task synthesis pipeline that mimics human curation. In the propose and prune stages, language models generate candidate instructions grounded in realistic daily workflows. Automated filters then eliminate duplicates, enforcing strict novelty thresholds. During the build stage, the pipeline synthesizes a dedicated Docker file, mock database records, and a deterministic bash script designed to verify task completion. Next is the test stage. A baseline model runs a trial execution inside the newly spawned container pod to verify that the environment boots properly and all necessary tools are accessible. If the trial rollout encounters broken dependencies or syntax errors, the refine stage deploys a diagnostic agent. This agent iteratively patches the container definition until the environment passes all checks. This pipeline removes the human element from environment construction. It enables the automated generation of thousands of solvable RL tasks for data-scarce domains. This bar chart displays the primary empirical result of harness-native RL training. On the complex OS World verified benchmark, OpenForge GUI reaches 37.7%, surpassing the Claude 3.5 Sonnet zero-shot baseline. The system achieves similar cross-domain results, hitting 72.3% on live web navigation through Web Voyager, and securing a 31.7% pass-at-1 rate on standard tool use via ClawEval. Trajectory audits reveal why these specific models improve. Monolithic, verbose harnesses cause context bloat, consuming tokens that ultimately dilute the policy gradients and slow down RL convergence. Lightweight harnesses with direct modular tool registration optimize significantly faster, allowing distinct behavioral shifts to emerge under reinforcement learning. First, the model learns tool specialization. Generic trial-and-error bash scripting drops by 8.7% as the agent transfers its preference to specialized API invocations. This graph tracks the emergence of self-verification. Under RL, the model independently learns to inspect modified files before terminating, driving pre-submission verification rates from 54% up to 81%. However, trajectory data also exposes a critical vulnerability. Even with RL, multi-step error recovery after a failed tool call stalls at just 42%. OpenForgeRL proves that we can close the open-source capability gap by properly aligning models directly with stateful production harnesses. But the data also identifies the primary hurdle. Solving autonomous error recovery remains the critical bottleneck for future agent research.